Hello, and thank you for joining me today as we begin our discussion on the periodic table, and we're going to talk about what are known as valence electrons to go along with that. And so with this video, my goal for you is to be able to explain the difference between rows and columns on the periodic table, and be able to define what a valence electron is and understand how they're important, why they're important, what they do for an atom, and then you'll be able to identify the number of valence electrons in an atom for specific elements on the periodic table. So let's get started. The periodic table was first developed in the 1800s by a fellow named Dmitri Mendeleev. So Mendeleev arranged his periodic table with all the known elements, which is shown here, by atomic mass. And when he did this, he discovered that there were chemical properties that happened over and over and over again. That, for example, lithium reacted a certain way, and then he listed them out and said, okay, these guys do different things. All of a sudden, sodium, hey, this does the same thing or a similar thing. And so he started his list over again and then expanded out by atomic mass and so on and so forth. He was the first person to really put this all together. And so he arranged his by atomic mass, but he's the one that set up the idea of a periodic table. And with his periodic table, you'll notice there are holes. There's gaps here for elements that we hadn't discovered yet at the time. And so he didn't see this as a big issue. He was like, okay, cool. There's got to be something that fits here. And so what he did was he used his table and the things he knew about the elements within his table to make predictions. And so he predicted this element he called ecosilicon had to exist. So ecosilicon is had an atomic weight of number 72. And a weight of 72, which puts it between arsenic and zinc. So his ecosilicon has to come somewhere in here. And because he called it ecosilicon, he thought it was going to go right here. Okay, so this is the element he's predicting things for. He predicted it would have an atomic weight of 72. The one we found actually has a weight of 72.59, pretty close. Density, 5.5. Actual density, 5.35. Pretty close. Valence electrons, 4 and 4, exact. Melting point, he said high. I would call 937 degrees Celsius really high. Color, dark gray, gray-white. This might be the most off he was in his entire prediction. When it bonds with an oxide, he predicted it was going to be one of these and 2 oxygens. It's currently one of these and 2 oxygens, so he was exact. The density of the oxide. The density of the oxide. He had 4.7, it was 4.23. Okay, maybe that's as far as he was off. Chloride, Cl4, Cl4. Density of the chloride, 1.9, 1.84. And boiling point, less than 184. Super close. So what was found was an element currently known as germanium. He called it ecosilicon. And when this was actually discovered, he argued with the guy that discovered it and said that he's got the properties wrong because his numbers didn't match and he believed in what he did. And so his table is pretty impressive. What he did is pretty impressive. Here's our current table. So we currently arrange the table by atomic number. So 1, 2, 3, 4, so on and so forth. There are a couple places. I believe these two would flip if we went by atomic mass. And I think these two would flip if we went by atomic mass. I want to say there's one more spot, but I can't remember it right offhand. There's a couple spots that'd be different, but it's still pretty close. But we currently arrange it by atomic number so that it's all consistent all the way through, makes life really simple, and makes all the properties line up as well. And so I kind of jumped the gun on this, but we arranged it by atomic number currently instead of atomic mass to make it consistent, easy to follow, and it matches the properties all the way across. With this table, because things line up and work out, we have different names. And so these are family names. Families are considered columns. So columns are known as families or groups, either one, or you can call them columns. I will typically use family or group instead of the word column. But your alkaline metals are this first family. Your alkaline earth metals are the second family. I don't worry about 13, 14. I really don't worry about nitrogen. Oxygen, they're called chalcogens. I'm not going to use that very much. The halogens, number 17, you need to be aware of and familiar with. And then the noble gases, Number 18. The other group I would like you to know is the transition metals here in the middle. And that's just those you need to be aware of. These guys are called the lanthanides because lanthanum is the first element. These are called the actinides because actinum is the first element. Not a big deal in my opinion. If you know these other five, you'll be fine. But they are called families. The reason they're called families is because just like you and your siblings look alike, these guys react the same. So the noble gases are very unreactive. Your halogens are highly reactive. Your alkali metals, highly reactive. Alkaline earth metals all react in a very similar fashion. And so your groups, your families, your columns, number 1 through 18, elements within it have similar properties. The reason they have similar properties is what we're going to talk about next. And so our current model of the atom is called the electron cloud model. And what has been come to be understood is that electrons within the atom have different amounts of energy. So there's a cloud, but there's different layers of energy. And so this dark shaded region, this is an energy level. That the electrons here have a certain energy. Electrons here have a certain energy. And so electrons closer to the nucleus have less energy than those farther away. Because they're closer, they don't need as much energy. And which is why you feel your lower energy levels first. Just like we are lazy and like to do the easy things first, atoms are the same way. Hey, come hold in here where I don't have to do much energy. I don't have to exert much energy to hang on to the electron before it fills its outer shell. The reason we have families and call them families is because elements in the same family have the same number of valence electrons, which are electrons in the outermost energy level. So valence electrons are electrons in the outermost energy level. So elements in the same family have the same number of electrons in the outer energy level. Those are called valence electrons. And so, for example, column 1, family 1, your alkali metals have 1 valence electron. Family 2 has 2 valence electrons. We're going to skip these guys. These are a pain in the butt. They all have 2, but that's beside the fact. Column 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and your noble gases have 8, except for helium. Helium's only got 2. But this is why we call them families. They all have the same number of valence electrons. And so it begs the question, how many do atoms want to have? How many energy levels are there? Let's start with how many energy levels are there? Nope, let's lie. How many electrons do atoms want to have in their outer energy level? And if these guys are unreactive, that's because they are stable, they're happy, and they have 8, which means that everything else wants to have 8 valence electrons. This is the goal, to have 8 valence electrons, except for helium, because it only needs 2. But everything else needs 8. So now let's go to how many energy levels are there? If we can have 8 valence electrons, but how many energy levels do I have? Enjoy George Bush. Let me pose a different question. How many rows are on the periodic table? If you look over here, we have 7 rows go horizontal. So I have 7 rows, which corresponds to 7 energy levels. There are 7 energy levels in an atom. Seven energy levels possible. With the outer shell, we want to have 8 electrons in it. As soon as we get 8 electrons in the outer shell, the atom is happy and starts to fill the next level. But this is atoms in the periodic table. So I would like you to answer these questions. How is the first periodic table arranged? How is it arranged today? Is it the same? Is it different? What are rows called? We didn't talk about this. Rows are called periods. So rows on the periodic table are called periods. What do they represent? That one you should be able to answer. What do we call columns? And what are important about columns? What do they tell us about an atom? So answer those questions. If you need a little bit of an explanation or are struggling with this, come see me. I'd be happy to talk to you and help you through it. Otherwise, I look forward to continuing learning about atoms in the periodic table with you throughout the rest of the semester. Well, thank you for your time and attention. Enjoy the rest of your day, and I will see you next time.